Okay, for those of you watching the recording, here's the bell ringer. Feel free to stop and try to think of things we can measure. And I think you'll be surprised at how little we can actually directly measure. So you can pause here and come up with your answer. Okay, hopefully pause there. So there are 3 things we can measure about stars. This is what we came up with. Number 1 is the color, right? You can see in this picture. Now, this picture has been edited somewhat, but you can see some stars are red, some stars are blue. These almost have a greenish tint. And this is manipulated a little bit, but it is true that you can see different colors of stars. We're going to talk more about it in a second, but the color is going to be incredibly important. You can measure the color. You can measure how bright they are. Some stars are very bright, like this star here is much brighter than this star over here. There's different reasons for that, but brightness is the second one. And the third is their position, right? And that's it. So everything we know about stars, that's what I'm trying to emphasize here. Everything we know about stars, everything we know about our universe is based on 3 pieces of information. How bright is the star? What's the color of the star? And where is the star? And that's it. That's all we have access to. But I hope you'll be impressed. I'm impressed by how much we actually know just based on 3 relatively small pieces of information. Okay, we're going to stop and watch this video real quick. So again, if you're watching this recording, you can stop and watch it on your own. Okay, so there's a lot. I mean, that video really does a good job of highlighting, I think, what are the most important things. But we're going to talk about here, first of all, this ideas of radiation. When we say radiation, you may have heard this term before. You may automatically think like, I don't know, something dangerous. Might think about the Hulk or some kind of superhero or something. Radiation is just something that everything is radiating energy. Radiate just means to let go or to expend or to expel. So all objects are emitting energy all the time. Well, I should say all objects that have a temperature emit energy at a specific time. The hotter an object is, the more energy. So it has hotter objects emit more energy, obviously, but the amount of energy is proportional to the temperature of the object. In other words, if we look at a hotter object, it's going to emit more energy. And energy corresponds to wavelength, right? So short wavelengths have a lot of energy. So basically, as the temperature of an object increases, it's going to emit shorter and shorter wavelengths, right? And that's what this graph here is showing, right? So this graph is showing. Let's check it out. Again, imagine this could be something you would see on ACT, like, right? So wavelength is down here. So this is the wavelength of light on the x-axis. On the y-axis is intensity, or really just how many of those waves are being emitted. So for an object that's 3,000 Kelvin, okay? Off to the side here, let's see if I can figure out 3,000 Kelvin to Fahrenheit. I don't know what that is. That's about almost 5,000 degrees, okay? So for an object that's 5,000 degrees, you're going to notice that, that's down here, 5,000 degrees. It's going to be emitting a lot of different energies, right? So it's going to be emitting some down here. This might be in the microwave. Probably the infrared is like right here, right? So something which is 3,000 degrees is going to be emitting a lot of energy in the infrared section. It's also going to be emitting, you'll notice, some energy in this section over here. Not a lot, just barely, but some. In other words, if you were to see this object, what you would see is it would be glowing this very like dull red, orange color. And as it heats up, it's going to be emitting, right? So notice the peak wavelength. This peak wavelength is going to shift as it heats up. This is called Wien's law. We're going to discuss it later. It's not super, it's the actual equation is not that important to us right now. But the point here is that as an object heats up, right? Notice its peak wavelength is shifting higher and higher, right? So at 6,000 degrees, you'll notice, or 6,000 Kelvin, I should say. At 6,000 Kelvin, you'll notice that the peak wavelength is actually in the visible portion of the spectrum. This object would be glowing quite a lot. In fact, this 6,000 degree Kelvin, that is 6,000 Kelvin, I should say, is the temperature of our sun. And you'll notice that the peak wavelength is somewhere in the yellow section. Well, when we look at the sun, it looks yellow to us. That's why, because it is this temperature. Other stars have different peak wavelengths, and they would appear different colors. A star which is cooler will look more red. And there's not one up here, but a star which is hotter would shift again, continue to shift into the blue. So when we look at stars, they emit a frequency based on temperature. As they get hotter, that frequency increases. So this example is perfect. Think about like an eye on a stove, right? Before you turn it on, right? Before you turn the stove on, it is still emitting light, even though you can't see it. It's just all infrared. I mean, everything, presumably it's at room temperature, everything in this room is emitting light at a specific temperature. Now, because we are warmer than room temperature, right? We're like 98.6 degrees or so. We are emitting light as well. And we emit more infrared light than, a table does that's in the room. So again, if you have an infrared camera, you could easily see people because we are basically light bulbs. We're infrared light bulbs. Okay, so before I turn this on, right, it's going to be, before I turn the eye on, it's still emitting light. It's just infrared, okay, and not that much infrared because it's just room temperature, at least compared to us. So then I turn it on, and let's say I turn it on high. Well, what you'll notice at first is nothing. I mean, it doesn't really look like it's changing, even though it is starting to increase, right? That peak wavelength is increasing. It's just emitting still infrared. But eventually you'll notice it'll start to be like sort of a very dull red color. What's happening there is it's kind of like it's shifting, right? So it's starting to actually emit energy in this red portion. Now that's not the peak. The peak is still strongly in the infrared. Again, this is not an accurate picture because remember this was like almost 5,000 degrees. So you're hopefully your eye or stove is not getting to 5,000 degrees or else it would be molten at that point and it wouldn't be very good. But the point is still here that maybe it's all the way down here, but some tiny little portion of it is going to be in the visible light portion of the spectrum. And so eventually as it heats up more, it'll go from like a dull red to sort of a brighter red, eventually to an orange. And that's pretty much where you top out on your stove. You might think it starts to look a little yellow potentially, but again, it'll mostly be this sort of orange color. So all objects are emitting light at different temperatures. And that's important because, again, that tells us a lot about stars based on what color light they emit. Okay, for objects that are more consistent, like a gas here, we can get what's called a spectrum. So basically, if you have like a certain amount of gas, let's say you had hydrogen gas and you were to heat it up, right? It would start to glow, right? And as it glows, it emits specific wavelengths of light. And this is related to what they were talking about in the other video, what are those stair steps, right? So there are different shells, like electron shells. And so as these electrons jump around these specific shells, you end up with very specific wavelengths being emitted that are unique to each atom, right? So there is some, you'll notice here that these all look slightly different. I mean, there's some that look, similar, but like for example, this right here, this strong sort of cyan color in hydrogen, right? This is a wavelength that is emitted by hydrogen, and it's unique, and it has to do with sort of the physical properties of hydrogen and where those electrons jump to and from in terms of the electron shells. But the point is that this is unique, and so this string of colors would be unique to hydrogen. This string of colors would be unique to neon, right? And that makes sense with us, right? Because you probably have seen a neon sign before. They look very like red. So whenever you heat up a gas, right, we just see the light. We can't see the individual. We see it all together. Just like when we, we have white light. We know white light is composed of all the different colors, but we don't see that. We just see white. Same thing here. This is being broken up by a spectrometer, or a spectroscope, I should say. We wouldn't see this with our eyes. We have to use the tool to see this. What we would see is just sort of this same color. Now, it would look slightly different. I think if I remember correctly, hydrogen looks kind of bluish, and neon looks red, but there are different lines for each different atom. Okay, I'm going to show you this video, which I think shows some of these spectral lines. So again, each of these elements has its own distinct spectral signature. Now in that video, that was kind of muddled, like we could see a green line or something, but it's hard to see. Like I don't see like these very distinct. Like I didn't see two different purple lines. The way that these spectra are created is using a spectrometer. So the spectrometer is able to take light and break it up into its distinct different colors and look at how strong those different lines are. So again, obviously our eyes are limited, so we can use tools, something we commonly do in science, to see things better. All right, so we're going to talk about our first observation here. The first observation we have that about our universe is that the universe is expanding. Okay, so 1929, Edwin Hubble used the Doppler effect to measure the velocity of galaxies around us. Let's look at how he did that. So first thing we need to discuss is sort of this red shift and blue shift. Okay, so this is a spectral line. It's actually an absorption spectrum, but it doesn't matter. Point is that there are these little lines here. Okay, and this might be the spectrum for, I don't know, maybe this is probably was one of the ones on the other one, but let's say this is hydrogen. Okay, so we know where specifically these lines are. Okay. And I don't have the spectral analysis up, but maybe like we know that this line right here is supposed to be at 480 nanometers, okay? And that's just what it is. It's always 480 nanometers. That's a property of hydrogen. But let's say we measure an object like a star, and we determine that this line, there's a line, so it's obviously the exact same pattern, but instead of this being 480 nanometers, its redshift, or in other words, is a little bit longer. So instead, this is actually 500 nanometers. It's a 20 nanometer shift. What could explain that? Well, we've recently talked about the Doppler effect. The Doppler effect is where there's a shift in wavelengths based on the relative velocity between two objects. So if this is shifted towards the red end, or what we would say is red shifted, it's longer, that can easily be explained by the Doppler effect. Obviously, this is actually hydrogen. I mean, it's the exact same signature. It's just moved over a little bit. So the amount it's moved over correlates to a shift, a Doppler shift, which we can use the Doppler equation to figure out how fast this object is going. And we call that redshift. Blue shift is the same thing, except it's shifted the other way. So instead of being longer, it's actually shorter. So instead of 480 nanometers, maybe it's 460 nanometers. Instead, it's shifted to the left. This would be called blue shift. And again, it can easily be explained because we know that if a frequency increases, whatever's emitting that frequency, which in this case is a star, must be moving towards us. And so this would be blue shifted. So when we talk about objects, when we talk about stars, if they're red shifted, it means they're moving away. If they're blue shifted, it means they're moving towards us. So this is a bumper sticker put about the American Physicist Society. If this sticker is blue, you're driving too fast. It's a joke about speed, because if you're driving really fast, it would be blue shifted. And so they're saying if it's blue, it's red, right? But if it was blue, then you're driving too fast. Of course, the joke is that to actually get to move fast enough where this would literally look like it was blue, you'd have to be moving some pretty significant percentage the speed of light. So that's the joke there. One more time, same thing. If there's this galaxy here, if it's not moving relative to us, it'll just be, here's the line where we expect it, because we know this is emitting hydrogen, it's hydrogen, and so we know where this would be, okay? But if it's moving away from us, it's red shifted. It's moved towards the red. It's longer. Again, it's moving away. It's a Doppler shift. If the galaxy is moving towards us, it's blue shifted. I want to just quickly point out that doesn't mean it's actually blue, or it doesn't mean it's actually red, right? The actual spectral line here would be yellow. But again, it's shifted from this kind of greenish color, so it's shifted towards the red. Likewise, over here, that we would say this is blue shifted. It doesn't mean it's blue, but it's closer to blue. This is like a more dark green than what we originally expected. Okay, so what Hubble's going to do is he knows a few pieces of data. He knows how far some of these galaxies are, and he's able to measure the apparent shift between us, right? So he's trying to figure out how things are moving. Because at the time, there was this kind of discussion over, okay, well, is the universe static? In other words, a lot of people thought the universe was static. It was unchanging. It was infinite, round forever, always will be. Nothing's really moving around. It's like kind of randomly moving around, okay? So if that was the theory at the time, if that theory was true, then what you would expect is, as you looked at different galaxies, you'd expect about how many of them would be redshifted versus how many would be blue shifted. Well, if it's all random, it's like 50-50. Half of them might be moving towards us, half of them moving away. But really, since everything's constant, you wouldn't get any kind of real definite thing, right? That was the theory, right? And so other people thought maybe things were coming together. Gravity's going to pull everything together. And so if that was expected, if everything's moving together, well, then everything would kind of be blue shifted. Okay, but if everything's not moving, then no shift at all. Okay, so what do we think that Hubble measured? Well, it's surprising. Every single galaxy that Hubble measured was moving away from us. Every single one. Every star they were able to measure was moving away from us. And, is also interesting note here, the further they were away, the faster they were moving. So how do you explain that, right? This is a conundrum. It's already unexpected, but okay, so we find out everything is moving away from us? I mean, what's going on there? How can everything, that doesn't make any sense. How can everything move away from us? And if it's further away, it's moving faster. I mean, how can you explain that? It's hard. I mean, I couldn't do it. If I asked you to explain, I think you would struggle to find an answer because it's a tough question. Everything's moving away, and everything that's further is moving faster. But there is a way you can explain it. And this brings us to a pretty famous analogy called the raisin bread analogy, okay? If you don't like raisin bread, it's fine. You can pretend this is a chocolate chip cookie, no problem. You can't explain all of this if you assume that the universe itself is expanding and getting bigger. So look here, right? These two, again, we'll go with the chocolate chips here. These two chocolate chips, right? I mean, they're only 1 centimeter apart. This is before you bake it, okay? So we're going to bake it, and it's going to expand as it bakes, of course, okay? So before they were 1 centimeter apart, okay? Then the cookie is baked, and now it's 2 centimeters apart. Okay, cool. So it looks like, from the perspective of this chocolate chip here, it looks like this chocolate chip moved away 1 centimeter. And if it took a minute, well, okay, let's make it more realistic. Let's say it took an hour. Then I can measure the velocity of this chocolate chip here to be 1 centimeter per hour. Okay, what about this one, though? Originally, it's 5 centimeters away. But, of course, all of that dough in between has expanded, and now it's 10 centimeters away. So what would the velocity of this one be? Well, that's easy. It would be when a total of 5 centimeters per hour. It's 5 times faster than this one here. It also happened to be 5 times further away. Interesting. Okay, what about this one here? It started out 16 centimeters away, and by the time it's done baking, now it's 32 centimeters away. Okay, well, again, let's measure velocity. It moved, obviously, 16 centimeters. In an hour, that's 16 centimeters per hour. Again, that's bigger than any of the others. And you can clearly tell this to be true with any that you measure. If you measure the distance here, it's going to increase. But is it really fair to say that... It's not exactly fair to say these chocolate chips are really moving. They're not, of course. What is happening instead? It's the stuff in between. It's all the dough is expanding as it cooks. And since there is more dough between these two chocolate chips, you have more expansion. And so it looks like it's moving further away, but of course, it's actually space in between that has expanded. This is the only way to really interpret the data that Hubble gave us. If every galaxy is moving away from us and the galaxies further away are moving faster, the only real reasonable explanation is that the galaxies aren't moving at all. Instead, it is space that is expanding between us. And so every day, right? Every day, space is getting bigger. That's what Hubble found. Space is expanding more every day. It gets bigger and bigger. And so, if you think about that for a second, if you went backwards, right? So, if today space is tomorrow, the universe will be bigger than it was today. If you go backwards, it gets smaller and smaller and smaller, until eventually you end up with a point where, I mean, all of the universe must have been basically in an infinitely small point. We'll come back to that later. I want to try to get to 2 more observations, so I'll pick it up a little bit. Okay, the second observation we have here. There's more microwave radiation there is microwave radiation throughout the entire universe. So in 1965, there were 2 scientists working for Bell Laboratories. Last names are Penzias and Wilson. They were trying to do communication things, so they were really trying to bounce signals off the atmosphere and have a radio receiver detect them. Obviously, this is 1965. This is before there were, many satellites in space. I think any satellites in space. I think maybe Sputnik had gone up recently, but there was nothing in space. So today, if you want to send a signal really far and you don't want to do it by cable, if you want to do it wirelessly, use a satellite. But there are no satellites, so again, at this time, they were trying to bounce them off the atmosphere. But the problem was they had built this. I'll show you the picture real fast. This thing right here. It's called the Horn. They had built this radio receiver, and it cost a lot of money to build. It was not very cheap. It was pretty expensive. So whatever, that's the price of doing business, research and development. So they had built this, and they turned it on, and there was just static. Okay, that's kind of annoying. So, they'd spent a lot of money on this. They tried to fix it. They tried a lot of things. Actually, there were some pigeons that were living inside of the Horn there. So there were pigeons that were living inside of here. So they hired somebody to go get the pigeons out and clean up all the poop that they had left because they thought maybe that was having an effect. Nothing they did was able to get rid of this hum. Well, eventually they had the only explanation they could have after trying to eliminate so many sources of interference is that this hum, this radio static, was coming from everywhere in the universe. It was coming from all places everywhere they pointed. It was the same. And so this came to be known, what came to be called what's called the cosmic microwave background. It's just this microwave radiation. It's between microwave and radiation that's everywhere in the universe. Quite strange. Where did this come from? I mean, that's a big question. Where did this come from? I mean, it's hard to say, right? So again, this is we're talking about this section right here. This is kind of where it was, right? And so, whatever it was, right? It was sort of like this leftover echo from previous, because it matched up really well with what's called a black body, right? So this idea of something that radiates energy, and that's what we were talking about earlier when we were talking about like those temperatures. As something is hot, or emits a specific wavelength. It matched really well with something that in the previously was really warm. What they had found was, right, so that there was this stuff that was coming from everywhere. Basically, they showed that it was it was a source, it was some sort of radiation that came from every place in the universe, okay? And then that's quite strange. And it's abstract, I get it's abstract, but basically there was just this radio signal that comes from everywhere, every place in the universe, and it seemed to be very old. It's, no matter where you would look, it came from all places, and it was very old. So we're going to come back to this. I'm probably going to skip this video for now because I want to make sure I get to my third point here. Okay, last observation. If we use spectroscopy, we can determine the ratio of the elements in our universe. Okay? So when we did that, here's what we found. Hydrogen here is an incredibly large portion of our universe. Helium is fairly large. Everything else is pretty small. You'll notice there's there's a small there's a little bit of oxygen and carbon, but like everything else is kind of like not very present. Here you can see this is the relative abundance of different elements. Hydrogen, helium, next highest is oxygen, looks like carbon, iron, right? So it seems to be that if you follow this trend, right, so this is the atomic number on the x-axis, so this is the elements, and this is the abundance. It's very clearly that there's a relationship that goes down like this right here. In other words, the heavier the element, the less there is in general. I mean, it doesn't quite go in order, but very, very strong correlation there. So as a percentage here, what we found is that hydrogen and helium make up 98% of our entire universe. Right, so 75% is hydrogen, 23% is helium. Everything else makes up 2%. And that's a big deal because you and I, we are that everything else, right? Our bodies are carbon-based, right? So we have carbon, we have a lot of oxygen in us, and we have a lot of hydrogen. Again, two of those three elements are some of those that were not very abundant, right? So all of these, you can see all of these, there's a very small portion. So what I'm getting at here is that when we look at these three pieces of evidence, right? So again, the three observations we make. One, the universe is expanding. Two, there's this cosmic microwave background radiation. It's everywhere in the universe. We don't know what it is. Three, the relative abundance of elements seem to indicate that there are many, like most everything is just the very simplest elements. And there's very little of the heavier, more complex elements. Okay? So if we're combining all this together, right, then what does this all mean? Well, there is a theory which explains all three of these things, right? That explains all three observations, and it's called the Big Bang Theory. And it was proposed in the 1930s by a priest in the Catholic Church. And it's, I guess it's sort of controversial sometimes. I know a lot of people maybe feel a little uneasy about it. But what it does is it is able to explain all three of these pieces of evidence completely, right? These sort of strange things like this idea that there's just microwave background, that there's just the signal throughout the entire universe. The Big Bang can perfectly explain what that is. This idea that the universe is expanding, I mean, that's what the Big Bang is. It's just an expansion of the universe. And then finally, this ratio of the elements, there's this thing called nucleosynthesis, is an explanation for how heavier elements get made. And again, it's explained perfectly using the Big Bang Theory. So we're going to start probably at the beginning of next week, we're going to look more specifically at the Big Bang itself. But in general, the reason why the Big Bang is currently accepted as the origin of our universe is because it can accurately explain all three of these pieces of evidence. And there are some people I think who would like to, have some other explanation or say like, well, I don't want to accept the Big Bang, which fine. I mean, you don't have to accept it, but if you want to have a scientific proposal, if you want to have some sort of scientific proposal to replace it, you have to be able to explain all of this observations, and that's not so easy to do. And that's why the Big Bang currently is the accepted theory, because it does accurately explain these three. Okay. So I'm going to go back and show you this video now because I know we do have a little bit of time. I'm going to show you this video over cosmic microwave background because it is kind of strange. And again, if you're watching this at home, I encourage you to look at that video now.